Looking at chapter 28, problem number 4. Excuse me, I've already gone through this problem on this paper, so I've already written down all the steps, but I'll still go through them all. What we're looking at in this case is an infinite slab of charge of thickness 2z naught. You can see that's this outer box with thickness 2z naught that lies in the xy plane. The volume charge density rho is constant in this case. And in part A, we're using Gauss's law to find an expression for the electric field strength inside the slab. So that's what this darker box represents. It's our Gaussian surface, a box in this case to represent this similarity to the slab. That is a smaller thickness, in this case 2z, not 2z naught, sorry, just 2z. And it's got, in this case I've written it with lengths L and W. So we'll start with the right side of our Gauss's law. The enclosed charge in this case is, because it's a constant rho value, is just volume times rho. Our volume in this case is the length L times the width W times this 2z. So the volume is L W 2z. And we can bring this down to the bottom. You'll see I've got it crossed out for our next step. LW 2z, this complete right side is LW 2z times rho over epsilon naught. We'll go over to this left side, and what we're looking for in this case is this double enclosed integral of E dotted with ds. That integral ends up being, you want value of E times the total surface area of flux. We'll call that S. In this case, the total surface area that we're interested in is only the top surface of this box and the bottom surface of this box, because those are normal to all of these E field vectors. These sides on here are oriented such that they won't have any flux, and so they won't affect the E field in this. And so what we can say is that this is E times this two of these, length times width. That's the total surface area that we're interested in. So 2E LW. Bring that down, 2E LW. You can see that this LW and the 2 will cancel out on each side. We come up with E equals rho z over epsilon naught. And that'll be true for whatever value of z you choose. In part B, we're asked to find an expression for the electric field strength above the slab. So that's when z is greater than z naught. In this case, on the right side, what we're looking at is just the total rho times the total volume of the infinite slab. In this case, enclosed charge is equal to L times W times 2z naught times rho. And so we can bring that down, erase this and rewrite it. L W 2z naught times rho over epsilon naught. On this side again, that E times the surface area value in this case again is just 2LW. So we've got E times 2LW equals LW times 2z naught rho over epsilon naught. In that case, 2LW cancels with the 2LW on this side. And we've got, for this case, E equals rho z naught over epsilon naught. It looks really similar to our answer from part A, only in this case, for any value of z that you choose for the height of this Gaussian surface, you're still going to end up with just the your E being equal to rho z naught over epsilon naught. That means for any thickness beyond this 2z naught, you're going to have this constant E value. And that'll come in handy here on part C, where we're asked to draw a graph of E while the thickness goes from 0 to 3z naught. And so we'll be looking at this for 0 to 2z naught. That'll be like our part A, where our value is equal to rho times our z value over epsilon naught. In this case, if our thickness is z naught, that means it's 1/2 of the thickness of the original. And so that'll be rho times z naught over 2 is our z value. And that's over epsilon naught, so that's our value at that point. When we get to thickness of 2z naught, that's exactly what we looked at in B. Anything at that point or greater even is going to be this constant rho z naught over epsilon naught. And so this is what our graph of E, and for any values here off greater than that, it's going to stay that constant value. And that is the complete problem 48 from chapter 28.